Hypothesis testing, where we don't know the variance of a population, is very similar to when we do know it. We're just going to change the statistic. It's going to be very similar to how we approached confidence intervals when we knew or didn't know the variance as well. Very similar and parallel kind of activity that we're following here. We're going to go back to the data from example DS 1.1 quite a while back there in module 6, associated with these aluminum test coupons. These specimens were being subjected to cyclic failure or cyclic testing until the number of cycles of failure developed. And we did that for a fairly large sample, in this case 70 different tests, and we're going to see how that plays out in this particular example here, where we're going to be interested in the mean number of cycles to failure, and that our null hypothesis is going to be that mu, our true mean, is equal to 1300 cycles to failure, and our alternative hypothesis is going to be that our true mean is not equal to 1300. You could just as equally have decided that you care about this on the low side or the high side, but we're going to go on the low side. Right now, underneath all of this, that we're going to assume that our individual tests or inherent population is normal with some unknown mean and some unknown standard deviation. Okay, so there's our hypothesis that we're testing, and we need to go decide what test statistic we want to use. And since we don't know the population variance here, we're going to immediately just go and take a look and consider that we'll use the t distribution here for associated with our sample mean. And so I'm going to adopt the notation of your your textbook and use the subscript t null. For what we're going to test for here, right? Now, again, n is large, right? It's on the order of 70. It's much larger than 40. We could use z equal to x bar minus mu naught over s over square root of n, and pretty much get to the same answer that we're going to be ending up driving at here. Right? Our significance level is going to be the common level that they so often use of 5%. Right? Again, that's somewhat arbitrary. It's more of a convention than anything else. And remember, that's going to be associated here that since we're on a two-sided kind of situation, draw our good old bell curve here, centered on 0 and two-sided. So we're talking about tail area, and so there's our t alpha over 2, and remember we have degrees of freedom associated with this. So there we've got that n minus 1 that's sitting in there. So this is going to be now equal to 2 times our tail probability that our statistic is outside of our critical value. And I put the absolute value in there just to be a little bit more mathematically precise about that, right? And our rule that we're going to have then is that we will reject the null hypothesis if our computed statistic is larger than, in this case, larger than this one, or of course if T naught is less than on the other side of us. So our computations, because it's the T distribution, and the T distribution is dependent upon the number of degrees of freedom that we have, is a little bit more complicated if you're processing this by hand. If you're using software, well, it's not really any more particularly complicated. But we'll show how you do this by hand. So for our computations here, we need to go get our T naught value. That's equal to x bar minus mu naught over s over square root of n. And so our x bar is our 1403.6 minus our mu naught of 1300 divided by our standard deviation of the sample, 402.4, divided by square root of 70. Right, and that is about 2.16. And we got to figure out what to compare that to. And again, when we go into our t-tables, remember we're going to have to deal with nu, which is equal to n minus 1. That's our degree of freedom here. So we have 69 degrees of freedom that we're working with. That's, of course, pretty large and puts us at the bottom of the table. And so note that you'll have a nu equal to 60, a nu equal to 120, and then for the alpha over 2, the tail area equal to 0.025. That's the critical thing. And note that the alpha I wrote down here is consistent with our significance level, not with the alpha that you see in that table. That can be kind of confusing. Our significance level was 5%. 5 divided by 2 gave us the 0.025. That's what you want to go into the table with. And under that, for nu equal to 60, we have 2.000. And under 120, we have 1.980. And then over here for alpha over 2 equal to 0.01, we get 2.390 and 2.358. And notice if you really wanted this t-value, then you could go in and you could determine crudely through linear interpolation, but it'd be better to use something else like software to come up with this. But we really only need the bounds, right? Our nu is equal to 69, so we're somewhere in between here. And note that that puts us somewhere in this sort of space that's been defined, if you think about this as a space, somewhere at this point for the associated t-value for our specific case. And since that's the case, what we can really do is we can come up with a bound, right, on the associated alpha, and that bound is going to be good enough for us, right? Because what we see here is that alpha or 2 will be bounded between here of 0.01 to 0.025, or obviously that means alpha is contained, the alpha that's associated with our, or I should say the p-value that's associated with that, is contained in the 0.02 to 0.05 region, right? So I want to change that real quick. I need to be more precise about this, that this is really the p-value that we're working with here, the p-value that goes with the particular statistic. Right, 0.02 to 0.05, and that's good enough, right? Because our statistic was, or excuse me, our significance level was 5%, and we know that our p-value is a little bit less than that, right? So we're outside of that region, right? So that's one way to look at this. The other way to look at this is that our t critical associated value here, our T alpha over 2 n minus 1, right? You can look at it as being, for our 0.025 value, is sitting up somewhere between 2 1.98 and 2. And we have a T0 value of 2.16. Right, so two different ways to sort of look at this. We had the rejection rule set up here, and we said that if our T naught is greater than T alpha over 2 n minus 1, right? And so what do we have? We have 2.16 is greater than, at most, 2.0 as a bound for our specific situation. It might be 1.98, it might be 1.99, it'll be somewhere probably between 1.99 and 2.0, but who cares, right? Because this is already larger. That already gives us a conclusion, and therefore we are going to reject H naught, which means that we're rejecting that mu is equal to 1300.